Okay, I'm going to speak to a slide deck that briefly describes the algorithm. So the protection range estimation problem, I think of it as a two-part problem, really. The part A, the first part, is like it acts like a portable calculator, and it produces a probabilistic estimate of the ECM protection range under combat conditions and in real time. And the key point here is that there are uncertainties about the attack scenario. Now, part B, I'll call it input conditioning. Now, the challenge here is for the device to determine the best possible set of input parameters. And I'll get to that shortly, but we're going to use essentially genetic algorithms or evolutionary algorithms to determine the range between the ECM and the antenna and the protectee and respective heights and antenna gains. That's the basic idea. And there's a video about this. So let's talk about part A, which is the calculator part. So the attack scenario looks like this. We have an ECM vehicle in this case with a transmit antenna, and there's an IED, a radio-controlled IED, a roadside bomb somewhere, and therefore there's a trigger man somewhere. And we know a fair bit about our own kit, but we really don't, although we know some things about the IED bomb and the trigger man, we don't know everything. And we certainly know less about, let's say, about the environment, because if it were a vehicle, then the environment can keep changing. Doesn't necessarily, but it can. However, we do know how signals propagate, and that's another video, set of videos. And so the idea here with the protection range estimator device is to use a propagation model with information about the environment and our own ECM and knowledge of the threat to determine the operational status of protectees that are supposed to be protected by the jammer. And by the way, this is an application for threat exploitation information. Here's a practical use for it because it's the information we have and the variabilities about the threat. So let's do a survey of some important parameters. Well, here's again it's an attack scenario. We need a reference point, and let's make that the protectee that's holding, for example, a ECM protection range estimator device on a cell phone or a hand or some sort of application device. So we need to know in order to calculate whether the protectee is safe or not, this is a thought experiment now, we need to know, for example, the ECM transmit, or specifically the height of the ECM transmit antenna. We need to know the height of the sensor antenna, the height of the IED receiver antenna, and the height of the trigger man's antenna above the ground. So we can use a propagation model. And so we're also going to need to know the range between the ECM and the sensor, between the ECM antenna and the IED antenna, and between the trigger man antenna and the IED antenna. Those are the things we need to know to do the calculations. But the most important part of this whole equation is that there are uncertainties. And so let's do a survey of possible methods for handling uncertainties. Kind of like the last one, actually. But before we do any of those things, let's take a closer look at the problem. Okay, so the most obvious of all the uncertainties, arguably, is that we don't know the height and range of the IED and bomb antenna, and we do not know the height or the range of the trigger antenna. Now, there's a whole bunch more, but those, to my mind, are the most obvious ones. But also, there are some things that we don't know with absolute moral certainty about ourselves. We don't know the exact height of the ECM transmit antenna or the receiver antenna at the protectee who's holding the device, and a bunch of other characteristics related to those too. Even though they're ours, we don't know them like to 10-digit precision. So basically there are uncertainties, and we're going to handle those statistically. And the key idea here, thinking now about the excellent question asked by somebody earlier about what do you do if you don't know where all the details of the attack? Well, uncertainties can be bounded. So let's use an example. Let's pick an example, and let's consider just the trigger man. Okay, the range between the trigger man antenna and the IED, the bomb antenna. We don't know that. But what do we know? Well, like, where is he? We do know that he's not here. He's not standing beside the vehicle because we don't let that happen. And, to be kind of funny, but it's still a true statement, he's not on the moon. He's definitely not that far away. So we also know that the transmitter has to be, let's say, 5 watts max. And maybe the trigger man The trigger person can see maybe a mile. Maybe you can see that far. So we could say, for example, that the triggerman can't operate farther than he can see because he's got to see when to click the go button when the victims are near the bomb. Maybe the triggerman can be anywhere from 50 to 500 meters. And in fact, in the similar kind of logic process, all the parameters can be bounded. All the parameters we need to do the calculation can be bounded. And we can argue all day about what the value of those bounds should be or shouldn't be and so on. But with absolute moral certainty, every single one of those parameters can be given a lower and an upper bound. Whether you agree or not, they can all be bounded. So, again, we're going to handle these things by statistically by using bounded values for all the parameters. And the solution that we're finally going to get out of this device is essentially the properties of the population of answers. And from information theory, that's just as good as you can get. If you can figure out where the triggerman is, or any of these things, and you can shrink those uncertainties down in those areas where you can get specific information. But you're still going to do the same essential process of calculating the statistical properties of a population of answers. So let's make this a bit more real. Let's say we have a driving route for a vehicle where there might be IDs. So the IDs could be anywhere here, like they're not going to be up on top of the mountain. They're going to be near the road. There's a bound. And the triggerman could be anywhere, in these areas, let's say, just as a thought experiment. And that means if we have those two things, we could apply the propagation model. We could do that. So that leads us to something I'll call the warning zone definition. That's the next thing to do. And a warning zone is the region, the distance from the ECM transmitter at which the ability of the jammer to prevent the trigger signal from being received by the bomb starts to get a little ratty. It's intermittent. So that's what I mean by the warning zone. And I'm going to cast the explanation in terms of a protection range estimator device, just to illustrate key points about how the counter ID ECM protection effectiveness prediction. Okay, so and here's where we're going. This picture, what we're looking for is the output, a software output, and it is the yellow region shown in this picture. Closer ranges than the inside edge of the warning zone, ECM is effective by definition, and beyond the farthest edge of the warning zone, ECM is ineffective. And since it's the transition zone, it's not just important, it's vital to have a clear definition of what's meant by the warning zone. Okay, so here's a test range to explain this. And we add ECM, and let's add a sensor, which is our protectee. It's where the protection range estimator device is. And we need to specify, because we want to calculate the ECM effectiveness, that's what the device is supposed to do. We need the sensor and the ECM antenna heights. We need the sensor to ECM range. And we need the relative ECM antenna gain relative to the sensor's receive antenna gain. We need to know those three things as a start. So let's place an IED and a triggerman on the test range and turn on the ECM. Now, so where the bomb is right now, I've just drawn it really close to the ECM transmitter. So let's say that when we do the experiment, this is a thought experiment, the trigger signal has no effect, the bomb does not go off. So at that range where the bomb is, the ECM is effective. Now, so move the bomb farther and farther and farther, and in each step we notice that it's just the trigger signal doesn't get through. But we'll get to a range where eventually where the ECM becomes intermittently successful. Beep, 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 like that.
In the middle of this image is an IED receiver on a wooden test stand. There's an ECM transmitter off to the right, and then trigger signal transmitter off to the left. And the IED receiver in the middle of this picture makes a whistling sound when it receives the trigger signal.
Service denial test. The receiver, which you're looking at now, is 80 meters from the transmitter, which is downrange, and 40 meters from the transmitter, which is here.
That's the IED transmitter.
And the effect depends on body position. If I block the transmitter,
the IED transmitter, the trigger transmitter,
there's no breakthrough. But when I stand fairly far away, there is a breakthrough, intermittent breakthrough. Now let's change it by a meter. Toward the jammer. We still have breakthrough. Another meter. Now it's 78 meters. Less breakthrough, or none, unless I stand in front of the jammer. Even a hand can do it. Should do, was doing it. Well, not in this case. That was a 2 meter change. And we having no breakthrough now.
And if we go any farther, the trigger signal gets through all the time, always. So there we have in one experiment defined the safe transition region and the unsafe region. But this is only for one possible attack scenario. There are other possible attack scenarios. For example, the trigger man is far away, or the trigger man is close, or the IED is an FRS radio, or it's a long-range cordless phone. All kinds of differences adjustments we could make to the possible attack scenario. So let's do it again in the thought experiment. Let's repeat the experiment for different scenarios. Here's attack scenario A, it's a long-range cordless phone. Attack scenario B, it's a FRS radio or a garage door clicker, and it's close range, or C, D, E. At each experiment, we get a different answer for the transition region of ECM effectiveness. So the spread of these transitions is the warning zone. And from this, and they're all caused by differences. Again, to hit it one more time, they're caused by this spread is caused by uncertainties in the attack scenario and the threat characteristics and so on. And we can use this spread, we can calculate a probability density function for the transition region. And so the warning zone information, the distance, is derived from this probability density function. Again, from information theory, this is as good as it gets. Unless you can find out more information about the attack, then you can narrow down that PDF. But this is the best we have with the available information. That's by definition what that blue line is. Now, the width of that yellow warning zone is determined by the confidence threshold or the confidence interval that you want. For example, maybe we want to know the width of the meaning of the warning zone is that with 95% confidence, the real ground truth in the day, in the moment, attack transition is within that yellow region. We don't know what it is, but we know we're 95% sure it's inside that window on the day of the combat mission, on the moment of the combat mission. And it's determined by the width encloses 95% of the area under the probability density curve. The probability density function. Or we could use maybe 80%, and in that case we only need to enclose 80% of the area so the width gets narrow, or maybe only 10%. Maybe we don't only care, we want only satisfied with the 10% probability. Again, it's a risk management. So if under certain conditions we're satisfied with 10% confidence, then okay, then the width is narrower. So there's a trade-off between uncertainty and certainty and width, depth of the warning zone. Okay, field trials results. Okay, so I built one of these things. It's 137 lines of 1,000 lines of code. It uses open source propagation model, and I tested it. I validated the propagation model. It looks solid, and it's a 700-page final report. I filed patents about all this, so if somebody is interested in picking this up, call me. Now, how well does this actually work? This device? Well, the answer is if the attack scenario is perfectly known, for example, during field trials, we could create field trials like this, then the protection range estimator device predicts the protection bubble to an accuracy of within about 1 or 2 meters over 120 meter test range. So pretty good under controlled conditions. Now, what proof is? You know what, before we pass this, why would we care about, you said good question, why would we care about how well this thing works under controlled conditions? Because we don't have controlled conditions in the real combat. Well, the reason is, because if it works under controlled conditions, then we can believe the predictions. There's that evidence that we can believe the prediction for the statistical case. Because each one of those statistical cases now, even though it's not happening in the real world, necessarily happening in the real world, the result is correct. So that means now, because it works under controlled conditions, we have reason to believe and put high confidence in the results of the statistical answer. And that's the one we need in combat. Okay, what proof is there that this thing works? Well, I did tests to measure the ground truth protection bubble size, and here's how it worked. There was an ECM transmitter, there was an IED receiver, and an IED trigger transmitter at the far end of the range. There were 3 attack scenarios, and this is the first attack scenario. I called it the collinear attack scenario because all 3 elements are on the straight line. And I looked at the ECM protection bubble size for a high power ECM transmitter, a medium power, and a low power. So the device should work for all those 3 cases, for example. Okay, so I checked that. The second attack scenario was I called them tower tests. So in this case, the IED transmitter was moved off the road and onto a wooden tower adjacent to the road. The ECM transmitter is on the road, and the IED receiver is also on the road, as in the collinear case. And so the situation looked like this. So you can pause the video and have a close look at this. I don't want to drag this any longer than I already have. I did that test. And I also measured the ECM protection bubble under those circumstances. You see a circle, a red circle here in the middle. Well, there's the red circle actually measured in a field. And yeah, it's not exactly a circle, but it's there. It can measure it. The third attack scenario, I called it a roadside ditch test and attack. And so anyway, we did that one too. But I won't talk about these. There's a video about all these results. So the overall conclusion, though, is, yeah, we know what's going on based on experimental results. So in conclusion, this video is my answer to the question, how do you calculate the ECM protection level without knowing the ERP and the position of the real-world trigger transmitter? And if something is unclear, then send me a message, and thanks for watching.